Okay, I can't be here. The program I tried to use didn't work right, so I'm trying it this way. So we're going to go over what you need to know for the test tomorrow. We've already talked to you a little bit about Minnie Mouse, and so you got to remember when Minnie Mouse is here. When Minnie Mouse is first here, she's got her little car, and there's no energy in her at all. So when there's no energy in her, what we have to do is put energy into her by doing work. We apply a force over a distance. We put in a big force and a little distance to pull her back. Then she goes zooming forward over a much bigger distance. The only way that this is going to work is if she's pushing forward with a small force. So I apply a big force over a small distance. She pushes with a small force and gets a big distance off. So the work out and the work in are equal. We're not getting magic energy from nowhere. She's not getting more work out than what she put in. Over here to this side of the board, there are listed what you need for problems A, problems B, problems C, and it says simple machine IDs. What I mean by simple machine IDs is I'm going to give you a drawing or a picture of a simple machine like we did on the lab. So you've worked through a bunch of these, you have practiced with these, you should know what you're doing, but let's practice one together. If this is a picture of a nail trimmer, then this is your nail clipper. You stick your fingernail in there and you get clipped. So when you're squeezing it, you're going to apply effort over here, so that's going to be your effort. This is where it's going to pivot as you push up and down. It's going to move from here, so this is my fulcrum. When I'm shoving this, what I'm doing is I'm shoving this down, so this is my resistance. So I have fulcrum, effort, resistance. Since R is in the middle, again we think of the word free, and since R is in the middle, that's the second letter, so this is a second class lever. And so if I want to find out what is my actual mechanical advantage here, then the difference from the F to the R is going to be my resistance arm. And of course the distance from the fulcrum to the effort is going to be my effort arm. And to find my mechanical advantage, I'm going to take the effort arm divided by the resistance arm. So that will tell me, in a perfect world, how much stronger I would get by using these clippers. So you'll have to do something similar to this on the test. You'll have to be able to measure this and this. You'll be able to identify what your parts are. You'll be able to tell me which class of lever it is. So you got made as far as that goes. If you look at your problem C worksheet, I'd like to go through the answers to this since you weren't here to see those. So now you'll be here to see those. Question number 1, to change the total amount of kinetic and potential energy in a system, what must be done to that system? If I'm going to change my kinetic energy or I'm going to change my potential energy, the way that that does that is potential can change to kinetic or kinetic can change to potential. But if I want to change either one of these, it's because I did work on it. So I'm either lifting it up, increasing its height, increasing its potential energy, or I'm shoving it sideways, increasing its speed, which increases its kinetic energy. Question number 2, most potential energy can be changed into kinetic energy. What other forms of energy can it be transformed into? The ones that we talked about in great detail the other day are sound, light, and heat. We talked about how when you drop the golf ball loses potential, turns into kinetic. When it hits the ground, it does work on the ground, and it doesn't bounce up to the same height because sound and heat particularly are given off when that collision occurs with the ground. Number 3, name 3 types of potential energy. We talked about nuclear, gravitational, and chemical potential energy. In this class, we're talking about gravitational potential energy. Number 4, as the Earth moves through its elliptical orbit around the Sun, it's closer to the Sun during our winter. At that time, it's also moving faster. Explain in terms of energy. Well, what happens is, we won't use Earth as an example because that's not much of an ellipse. If we look at, say, Pluto, Pluto has an orbit that's much more like this. If the Sun is here, then at part of Pluto's orbit around the Earth, it's much farther away from the Sun, part it's closer. At the closer part, we have less potential potential energy because it has a smaller distance that it can fall. Think of the distance away from the sun as the height. When it's over here, we have more potential energy because I have farther distance from the sun. I can fall a farther distance. So if I have more potential energy here, then I have less kinetic energy here, which means Pluto is going to be moving slower. Over here, if I have less potential energy, I need more kinetic energy, which means Pluto in this section is going faster. And that's what happens. If I have less potential, I have more kinetic, which means I have less height, more speed. Here I have more height, less speed. I'm going slower. Moving on to number 5. Chuck drops a ball from 8 meters. If the ball does not bounce, what kind of collision is it? If it smacks and doesn't bounce, then that's an inelastic collision, and all the energy would turn into sound and heat. If the ball does bounce, it's going to be an elastic collision. It will only bounce back up to its original height of 8 meters if it can collide with the Earth without producing any sound or heat. And of course, that's just stupid. That's not going to happen. Since sound and heat are produced, we don't expect it to bounce up to the same height it came from. Number 6. A major source of electricity in many parts of the world is hydroelectric dam power. How do dams get energy, and how do we get the dam energy? The way we do this is we have a river that's flowing nice and slowly downstream, and gravity's pulling it down the hill. What we do then is we take a large concrete barrier and we stick this concrete barrier in the way, and the water starts to slowly fill in behind it until finally the water is way up here. If we suddenly have this huge height of water back here, then we have a huge amount of potential energy that's in the water behind the dam. If we have all this potential energy behind the dam, then what happens is I can open up a little hole through the dam. If I open up a hole through the dam, then all this water, instead of trickling slowly like it did before down the stream, the water is going to come shooting out of here at a very high rate of speed because it has a lot of kinetic energy depending on how much height the potential energy has. So this potential turns into kinetic. We get a lot of speed out of here. Now, how do we get the energy out of that? Well, the way we get the energy out of that is we stick a little fan blade in here, so as the water's coming by at a high rate of speed, it spins our fan. Our fan is connected to a big electric generator, and we generate electricity, and everybody's happy. Okay. As far as the problems go, I'm going to let you work on all of them except number 9 and 10. 9 and 10 are the ones that are most crucial to the test, so that's what we will focus our attention on now. So in number 9, we have Oscar shooting an arrow. So here we have the ground, here we have Oscar. He is holding on to his arrow. So his arrow is 0.10 kilograms. That, of course, is a mass. The arrow is 1.5 meters off the ground. He's going to pull back with a force of 298 newtons, and he's going to pull back for 0.65 meters. So 298 newtons, of course, is my force. 0.65 meters is my distance. If I have force and distance, of course, that means I did work. So when I grab the arrow and I pull it back, I did work on the bow. When I did work on the bow, I loaded the bow with potential energy. So what we're saying is I did work that increased my potential energy of the bow, but then when I let go of the bow, then all that energy turned into kinetic energy of the arrow. Now, even though we did stop at the potential energy intermediate, we don't really care about it because it doesn't help our calculations any. So we're going to take the work. We know work is force times distance, and we're going to say that work turned into kinetic energy, and v squared over 2 of the arrow. If we know this to be true, then we should be able to solve for v. So 2 goes from the bottom on this side to the top, m goes from the top on this side to the bottom, and then to get rid of this thing, we want to have that thing. So what we're going to do now is take the square root of 2 times our force, which was 298, times our distance, which was 0.65, divided by our mass, which we said was 0.10. And so if we stick that all in underneath the parentheses, we find out that we went 62 meters per second. So you can check that out and see if that's true. The second part, this is the part that's most important for the test. If we just stop right here, as long as you understood, hey, the work turned into kinetic energy, I throw them equal to each other, I solve for V, you're in great shape for the test. If we're worried about actually solving the second part of the problem, of course, when he lets go of the arrow will travel in a parabolic trajectory. We want to know how far over it goes. That's going to be dH, which we know is VH times T. The VH we just figured out was how fast is the arrow traveling sideways. The T we're going to figure out from, remembering all the way back to Unit 5. Time down is 2 dV over G. So the dV is how far did the arrow fall? Of course that is 1.5 meters. So if we plug this mess in, we get 0.55 seconds that it falls. So that is our VH times T, VH times 0.55 means I get to go a whole 34 meters over until I go thump into the ground. So that is how we do number 9. Isn't it crazy? And again, the second part, I don't expect you to remember everything from Unit 5, but I do expect you to be able to do this section. Moving on to number 10. If we're looking at number 10, what we have is a slide. The slide was inclined to 43.2 degrees, that's a 4, and it was 3.8 meters long, and we have Trey sitting up here, ready to slide down the slide. He has a whopping mass of 47.3 kilograms, and when he gets to the bottom of the slide, he is going 6.38 meters per second. So up here he's just sitting, down here he's going zoom. What we want to know is what percentage of his potential energy was converted to heat. Well, to solve this, we're really going to have to do a couple simple problems. The first one is, what kind of energy does he have at the top? Well, of course, at the top he has potential energy. And potential energy is just mgh. We know the M is 47.3. We know G, of course, is 9.81. The height is going to be the height. Well, we have the hypotenuse here. On the test, you won't have to do an angle on this particular problem. I will give you a straight up and down problem. But in this one, we want to know this side, which is the opposite and hypotenuse. So we're going to use the sine. So we're going to have the hypotenuse times the sine of the angle, 43.2. So again, we use sine whenever we're going up and down. We generally use cosine when we're going side to side. But we have our mgh. And that will, these two together will tell me what my true height was. If I do that correctly, I get 1,207 joules at the top. So 1,207 joules is what we have at the top. Well, of course, when we say how much energy do we have at the bottom? Well, at the bottom of the slide, we have kinetic energy, not potential energy. And we know that kinetic energy is equal to mv squared over 2. He has the same mass he had before, 47.3. Here it said that he was traveling 6.38 meters per second over 2. And if we multiply that out, I believe it comes out to 963. So, here we had 1,207, now we only have 963 joules. We seem to have some energy missing. In a perfect frictionless world, then the amount of energy we have at the top would equal the amount that we have at the bottom. That works great if you're dropping something. Here he's sliding. So if he's sliding along here, then some of the energy seems to be missing. How much of this energy seems to be missing? Well, we had 1,207 at the top. We have 963 at the bottom. That gives me 244 joules. That seems to be missing. We put missing in quotes because, of course, it's really turned into heat. Where does that heat go? Mostly into trace tuchus. So as he's sliding down here, his butt's getting a little warmer, the slide's getting a little warmer, it's turning into heat. How much of it? This would be all I care about on the test. On the problem, though, I asked you what percentage is turned into heat. So, of course, percentage is how much are we missing compared to how much did I have to begin with. So I'm missing 244 joules. Originally I had 1,207 joules. So if we divide those, and of course times 100 since it's percent, that's going to give me 20% of his energy went into warming up his butt. So that's pretty much all we need to know for the test. The test is very, very straightforward. You're going to have to, I can plug into the work equation, I can plug into the power equation, I can plug into potential, I can plug into kinetic. I know